on a bus.
And one such flash of inspiration led to an early success. In 1885, King Oscar II of Sweden and Norway offered a prize of 2,500 crowns for anyone who could establish mathematically once and for all whether the solar system would continue turning like clockwork or might suddenly fly apart. If the solar system has two planets, then Newton had already proved that their orbits would be stable. The two bodies just travel around in ellipses around each other. But as soon as you add three bodies like the Earth, Moon and Sun, the question of whether their orbits were stable or not stumped even the great Newton. The problem is that now you have some 18 different variables, like the exact coordinates of each body and their velocity in each direction, so the equations become very difficult to solve. But Poincaré made significant headway in sorting them out. Poincaré simplified the problem by making successive approximations to the orbits, which he believed wouldn't affect the final outcome significantly. Although he couldn't solve the problem in its entirety, his ideas were sophisticated enough to win him the prize.
He developed this great sort of arsenal of techniques, mathematical techniques, which, in order to try and solve it. And in fact, the prize that he won was essentially really more for the techniques than for solving the problem.
But when Poincaré's paper was being prepared for publication by the King's scientific advisor, Mittag Leffler, one of the editors found a problem. Poincaré realised that he'd made a mistake. Contrary to what he'd originally thought, even a small change in the initial conditions could end up producing vastly different orbits. His simplification just didn't work. But the result was even more important. The orbits Poincaré had discovered indirectly led to what we now know as chaos theory. Understanding the mathematical rules of chaos explain why a butterfly's wings could create tiny changes in the atmosphere that ultimately might cause a tornado or a hurricane to appear on the other side of the world.
So this big subject of the 20th century, chaos, actually came out of a mistake that Poincaré only spotted at the last minute.
And so the essay had actually been published in its original form and was ready to go out. I mean, in fact, Mittag Leffler had sent copies out to various people, and it was to his horror when Poincaré wrote to him and said, stop,
Oh my God, this is every mathematician's worst nightmare.
Yeah, absolutely, pull it.
Yes, hold the presses.
So in a way, it kind of worked.
Owning up to his mistake, if anything, enhanced Poincaré's reputation. He continued to produce a wide range of original work throughout his life. Not just specialist stuff either. He also wrote popular books extolling the importance of maths.
Here we go, there's a section on the future of mathematics, which starts, if we wish to foresee the future of mathematics, our proper course is to study the history and present the condition of the science. So I think Poincaré might well have approved of my journey to uncover the story of maths.
He certainly would have approved of the next destination, because to discover perhaps Poincaré's most important contribution to modern mathematics, I had to go looking for a bridge. 7 bridges, in fact. The 7 bridges of Königsberg. Today, the city's known as Kaliningrad, a little outpost of Russia on the Baltic Sea, surrounded by Poland and Lithuania. Until 1945, however, when it was ceded to the Soviet Union, it was the great Prussian city of Königsberg. Much of the old town, sadly, has been demolished. There's now no sign at all of 2 of the original 7 bridges, and several have changed out of all recognition.
This is one of the original bridges. It may seem like an unlikely setting for the beginning of a mathematical story, but bear with me.
It started as an 18th century puzzle. Is there a route around the city which crosses each of these 7 bridges only once? Finding the solution is much more difficult than it looks. It was eventually solved by the great mathematician Leonhard Euler, who in 1735 proved that it wasn't possible. There couldn't be a route that didn't cross at least one bridge twice.
He solved the problem by making a conceptual leap. He realised you don't really care what the distances are between these bridges. What really matters is how the bridges are connected together. This is a problem of a new sort of geometry of position, a problem of topology.
Many of us use topology every day. Virtually all metro maps the world over are drawn on topological principles. You don't care how far the stations are from each other, but how they're connected. There isn't a metro in Kaliningrad, but there is in the nearest other Russian city, St. Petersburg.
The topology is pretty easy on this map. It's the Russian I'm having difficulty with. Can you tell me which...
What's the problem?
Want to know what station this one was? Oh, I had it the wrong way round even.
Although topology had its origins in the bridges of Königsberg, it was in the hands of Poincaré that the subject evolved into a powerful new way of looking at shape. Some people refer to topology as bendy geometry, because in topology, two shapes are the same if you can bend or morph one into another without cutting it. So, for example, if I take a football or rugby ball, topologically they're the same, because one can be morphed into the other. Similarly, a bagel and a teacup are the same, because one can be morphed into the other. Even very complicated shapes can be unwrapped to become much simpler from a topological point of view. But there's no way to continuously deform a bagel to morph it into a ball. The hole in the middle makes these shapes topologically different. Poincaré knew all the possible two-dimensional topological surfaces. But in 1904, he came up with a topological problem he just couldn't solve.
If you've got a flat, two-dimensional universe, then Poincaré worked out all the possible shapes you could wrap that universe up into. It could be a ball, or a bagel with one hole, two holes, or more holes in. But we live in a three-dimensional universe, so what are the possible shapes that our universe could be?
That question became known as the Poincaré conjecture. It was finally solved in 2002 here in St. Petersburg by a Russian mathematician called Grisha Perelman. His proof is very difficult to understand, even for mathematicians. Perelman solved the problem by linking it to a completely different area of mathematics. To understand the shapes, he looked instead at the dynamics of the way things can flow over the shape, which led to a description of all the possible ways that three-dimensional space can be wrapped up in higher dimensions. I wondered if the man himself could help in unravelling the intricacies of his proof. But I've been told that finding Perelman is almost as difficult as understanding the solution.
The classic stereotype of a mathematician is a mad, eccentric scientist, but I think that's a little bit unfair. Most of my colleagues are perfectly normal. Well, reasonably.
But when it comes to Perelman, there's no doubt he is a very strange character. He's received prizes and offers of professorships from distinguished universities in the West, but he's turned them all down. Recently, he seems to have given up mathematics completely and retreated to live as a semi-recluse in this very modest housing estate with his mum. He refuses to talk to the media, but I thought he might just talk to me as a fellow mathematician. I was wrong.
Well, it's interesting. I think he's actually turned off his buzzer. Probably too many media have actually been buzzing it, and I tried a neighbour, that one rang, but his doesn't ring at all. In some sense, I think that it's his papers, his mathematics, which speaks for itself in a way. I don't really need to meet the mathematician. And in this age of big brother and big money, I think there's something rather noble about the fact that he gets his kick out of proving theorems and not winning prizes.
One mathematician would certainly have applauded. For solving any of his 23 problems, David Hilbert offered no prize or reward beyond the admiration of other mathematicians. When he sketched out the problems in Paris in 1900, Hilbert himself was already a mathematical star. And it was in Göttingen in northern Germany that he really shone.